Today we're going to be talking about changes in lengths of axially loaded members, which is related to what we studied just briefly in Chapter 1, but we're going to go into more detail today. So what we're going to be looking at is how do we relate the elongation of a member to the applied load, the cross-sectional area, and any material properties that we might have. Okay, so we're talking about changes in length of axially loaded members. Okay. So the equation, the main equation that we're going to introduce today, the new equation, is the following. Delta, the elongation, is going to be equal to PL over EA. Okay, and so let me go ahead and derive this quickly for you using the equations that we've already learned in the class. We have that the normal stress, sigma, is equal to P over A. Okay. We also have that the strain is equal to delta over L, and we have that the normal stress can be related to the normal strain through Young's modulus epsilon. Okay, so using these three equations, what this yields is that P over A has to be equal to E delta over L, and then rearranging to isolate delta gives us that delta is the equation that we want, PL over EA. So you can see that we haven't done anything new here. We've just combined the three equations for normal stress and normal strain and elongation that we've learned in the first chapter of the book to come up with this new equation here. All right, so let's take a look at what this equation means in two different contexts. Okay, the first one, so we'll draw a graph here, where here we'll have the applied load P and delta here. Okay. All right, so we can create a line here where the slope of this line is going to be EA over L. Okay. And that comes from a slight rearranging of this equation here, where we then, instead of just looking at delta, we look at P is equal to EA over L delta. Notice that this equation here is just a rearranging of this equation here. There's nothing different here. This EA over L is often called the stiffness of the system. Okay, another way of looking at this is we can draw another graph, and instead of putting the load P on the y-axis, we can put delta on the y-axis and put P on the x-axis. And again, it creates a line, and here we're just using this equation directly. Delta is equal to P is equal to L over EA times P. Okay, and then this is the slope of the line, L over EA. Okay, and this sometimes is called the flexibility. They're just inverses of each other. Okay, so it's just vocabulary. It's not terribly significant. It's just a rearranging of this basic equation here and looking at the linear relationship between P and delta. Okay, and so it's important to know how to derive this equation, PL over EA, from these three equations over here. That's an important thing to understand. And then understand that it's just nothing more than a linear relationship where the slope is given by the geometric parameters and the material parameters. Okay. Now we're going to talk about a slight generalization of this idea, and we're going to ask the question, okay, what happens if the bar, so when we wrote down delta is equal to PL over EA, the kind of the geometry of the problem is we've got some bar, right, subject to a load, right, it's fixed, let's say on one side, and this load is applied at this end. This is the length L, okay, cross section here is A, and E is the material that the bar is made of. Notice that this bar, these values, so E, the material doesn't change from left to right, the cross-sectional area doesn't change from left to right, and the applied load P is constant from left to right. Okay, so this is a very simple scenario. The question is now is what happens under non-uniform conditions? Under non-uniform conditions. Okay, what happens under non-uniform conditions? Meaning one of these parameters now is either like a function of x, or there's a discontinuity where it goes from one value, then suddenly jumps to another value. How do we apply this equation here under those conditions? Okay, well, let's take a look at an example to help us develop some understanding of this scenario. Say we have a bar that's fixed up here like that. And we have loads now applied at several different locations. So we have P naught here. And let's say that we've got P sub C there. And up here, we've got P sub B. Okay. And then this length here we'll call L1, and then this length here we'll call L2, and this length here we'll call L3. So the question is if I apply these loads, these different loads at these different locations, what is delta? That's what we want to understand. Is there a generalization of this equation up here, delta equals PL over EA, that allows us to have these non-uniform loading conditions? Okay, so the first step is we use statics. Okay, so the first thing we're going to do is we're going to determine the internal forces. We're going to determine the internal forces in each section. Okay, what that means is that we're going to make a cut here, here, and here, and solve for the internal forces. And we know that by the way this thing is loaded, that those internal forces will be constant within each individual section. There'll be a jump as you move across this discontinuity, but it will be constant within each subsection. Okay, so why don't we take this cut first? So we'll cut it here, draw our bar again. Okay, we've got, again, P sub B, and then we've got down here P sub C and P naught. So the question is using statics, what is this value? We'll call this N1 for internal force. What is N1? Okay, so just using statics, it's very simple to see that N1 has to be equal to minus PB plus PC plus P naught. Okay, So now we know the internal force. Let me see if I can change colors here. So now we know the internal force in this member here. Okay, so we figured that's what N1 is going to be constant in this section here. Okay, and now we have to figure out N2 in this section. So let's go ahead and do that. And again, we're just going to take another cut. Okay, but this time we're going to take it somewhere in here. It doesn't really matter because it's constant, so anywhere between the application of PB and PC. And then we have P sub C and P naught, and N2 in this case is equal to P sub C plus P naught. Okay. All right, so what we've done so far is we now have the internal force N1. This equation corresponds to the internal force here. It's going to be constant in this subsection. This equation corresponds to the internal force along this whole subsection. And so now we're just left with this one last subsection here. Let's go ahead and do that quickly. So we make one last cut. We've got a short bar here. We have P naught, and N3 is just equal to P naught in this case. Now we have our three equations from statics that tell us the internal forces in each section of the bar. Now I want to reiterate that the internal force N1, internal forces N1, N2, and N3 are constant in the cross-section in which we computed them. So N1 is constant along this entire guy, N2 is constant along this entire guy, and N3 is constant along this entire guy. Okay, so that completes this thing here where we've determined the internal forces, and we've just, at this point, used statics. Okay, now the next step, step 2, is going to be determine the delta i's, right? Delta 1, delta 2, delta 3. So we want to see what each load does in terms of the elongation, right? Because you're going to have some elongation from N1 in the top subsection, some elongation from N2 in the middle, and some elongation from N3 in the bottom. Okay, and this is just, again, now we can go back to this equation that we described at the very beginning and just use it directly in each subsection, because P is constant. The ends are constant in each cross section. So delta 1 is equal to N1 L1 over EA. Delta 2 is equal to N2 L2 over EA. And delta 3 is equal to N3 L3 EA. Okay, good. Now, as you might guess, to get the total elongation delta, you just add up the contributions from delta 1, delta 2, and delta 3. Okay, so that's the third and final step. The final delta is delta 1 plus delta 2 plus delta 3. Okay, so let me see if I can summarize this. We began with this very simple equation here, okay, which corresponds to a bar where P, E, and A are constant along the length of the bar. Okay, that's a very important point. P, E, and A are constant along the length of the bar. That's when you can apply this equation directly. Okay, then we ask the question, okay, what happens if you have loadings, these point loads applied throughout the length of the bar? We call this a non-uniform condition. Okay, and the non-uniformity now is going to be in the internal forces that develop within each subsection. So we go through using statics, making simple free body diagrams to determine N1, N2, and N3. Okay, so that's statics. Then we apply the equation, the basic equation, within each subsection, because within each subsection, N1, N2, and N3 are constant within each section in which we're applying them. And then the third and last step is we simply sum them all up. Okay, so that's how we handle this type of non-uniform condition. So now let me ask you the question, so we have this, we just looked that the total delta is going to be basically, right, we're going to sum over all of the delta i's, right? What would happen, so in this case, in the case we just looked at, I went from 1 to 3, right? So this summation means delta 1 plus delta 2 plus delta 3. Now, what happens if delta is equal to a sum where I equals 1, but let's let it go all the way to infinity? Okay, what this means here, the symbol we use, we don't write 1 to infinity. Instead, we just use an integral. So an integral really is an infinite sum. Okay. And then we can basically sum up all the little delta pieces. From whatever, 0 to whatever you want to, whatever the length of the bar is, okay? All right, so in general, if we have the fully general non-uniform case, the equation is delta is equal to the integral n, which is now a function of x, dx, over e a of x. And in fact, e can be a function of x too. Okay, so everything can be a function of x. In the case where we have like basically fully non-uniform conditions, this thing can vary with x. Material properties can vary with x, and the cross-sectional area can vary with x. So if you can figure out these equations, you can do a very general calculation to determine the total elongation of a bar. Okay, so this would be like what I would call a fully general non-uniform setting. Okay, for bars and tension and compression. Okay, and you'll have an opportunity to do some of these in your homework, where there'll be some simple calculations you have to figure out for these equations for A and N. Usually it's just for A that we focus on. Okay, so let's do a problem now. Let's say we have the following setup. We have an object. Looks like this. And then we have a smaller cylinder. Off. And then we have a hole into here, like so, something like that. Okay, we're going to call this distance from the left to the end of this blind hole, we're going to call that L over 4. From here to here is another L over 4. And then this whole distance here is L over 2. This here will be diameter D2. This will be diameter D1. Okay, and this diameter in here, we're going to call it D max, and we'll use it later in our problem. And then there's going to just be an applied load P acting through the centroid of this object. Okay. All right. Now let's ask a couple of questions of this setup here. So the first question we'll ask is if the shortening of the bar is limited to delta A, what is the maximum allowable diameter D max, where D max is the diameter of this blind hole? Okay. Okay, so if you notice, we have three different cross sections. We have this cross section here that has a hole cut out of distance of length L/4. Then we have a solid circular cylinder for another L/4, and then we jump down to a smaller cylindrical bar of length L/2. Okay, so we anticipate that the final delta, as we did before, should be delta 1 plus delta 2 plus delta 3. Okay. All right, in this case, delta 1 is just going to be P, and then the length is L/4 over E, and we'll say A1. A1 is going to be the area of this guy right here, over here, plus P, length is again L/4, and then E A2 plus P L/2 over E A3. Right? Now A1, the area of this cross section where we have a hole cut out, is just pi/4 times D1 squared minus D max squared. A2 is pi/4 D1 squared, and A3 is pi/4 D2 squared. Okay, so you take A1, you plug it in here, you take A2, you plug it in there, and you take A3, you plug it in there, and then you solve for D max. Okay, and then you set delta. Remember, delta is given. Delta is delta A, and so our unknown now is not delta, because that's given, but we're going to back solve for D max over here, okay, when we plug everything in. Okay, great. So that's how we solve that problem. Let's do one more variation of this guy. Let's say we want to answer the following question. If D max is set to half of D2. Okay, so now we've put a constraint on what D max can be. At what distance B is going to be measured from the right end. Okay, so this is going to be B. At what distance B from the right end should load P be applied to limit the bar shortening to delta A. Okay. So this is slightly different. Now, d max isn't a variable. It's not an unknown. It's set to d2 over 2. But now the variable is the point of application of load P on this right end. Okay, so again, it's very similar to what we did before. Delta A is going to be given, so that's our total elongation. And then again, we have 3 sections. The first 2 sections are going to be identical to what they were before. So P L over 4 over E A1 plus P L over 4 over E A2. But now the point of application of P is going to be somewhere over here, right? So P is being applied some distance B from the left end. So this section here now is L over 2 minus B. So we have P, and then the distance is L over 2 minus B over E A3. Okay, so you plug everything in again, all the area, cross-sectional areas you plug in. D max now is known, and then you solve for B. So it's very simple, very similar to what we just did.